I will make a introduction in Spanish. Okay. ¿Qué? Bueno, bienvenidos. Para los que están acostumbrados a las reuniones de ARQCONF, esta es una reunión rara, diferente a las que venimos haciendo las 3 primeras que hicimos. No vamos a hacer la mecánica de workshop que hicimos siempre. ¿Por qué? Porque tengo una presencia de 2 speakers muy grosos, Mauricio y Salvan, que nos propusieron hacer una charla sobre microservicios, el uso que están haciendo de Docker y las modificaciones que están haciendo de Docker, porque se ve que no les funcionaba como ellos querían, entonces tuvieron que modificarlo un poco. Entonces, sobre es un arquitecto de Medallia, y directamente de Palo Alto, y que vamos a contar con su experiencia. Y él es un software engineer de Medallia, y entre los dos nos van a contar su experiencia con microservicios y Docker. Después de la charla, va a haber una serie de preguntas, como dijeron, y acá hay preguntas. Tengo que regalarme una regla, ¿no? ¿Era así? Pero tiene que estar buena la pregunta. Y no puede ser cualquier cosa, no puede ser como es el nombre ni qué es el nombre, no, esas cosas. Tiene que ser pregunta bien fundamental. ¿Okay?
Awesome. Okay. So I should probably let you all know I don't speak Spanish. I do apologize. So I think I should say thank you at this point, but I'm not really sure. So why don't we get started? So what we're going to talk about here is running microservices using relocatable Docker containers. Because we have built, or are building, a large microservice-based architecture. And one of the problems we run into is that it's one thing to have a beautiful whiteboard full of tiny little boxes and how they communicate and so on and so forth. It's another thing entirely to actually put this into practice. Works great on your laptop and you try to run it there. And then you go to the corporate data center and it says, really, the question is, what do you do if the hardware fails? And Docker is a wonderful technology. It's built by developers for developers. It has really awesome tools to build stuff. When it comes to actually running it, there's a few gaps. We have addressed those gaps for the scenarios that we have, and that's what we'd like to talk about here today. So let me actually first say 2 words about who Medallia is. If you go look at our website, we are software to improve the customer experience. And what we actually do is that we aggregate billions of documents in a second or less. So the infrastructure that we and the architecture we're presenting here today is the stuff we have built to run all of these crunching applications. And the wonderful thing about that is that, hey, infrastructure is not our core product. We built this to support what we do. So we actually want as many people as possible to do the exact same thing. So all the stuff we're presenting here today, you can download the source code, entire configuration, everything you need to run the exact same setup. So the problem we want to solve is that we want a reliable and flexible data center. And we love Docker. We want to run Docker for absolutely everything. We run Docker for applications. That's been done. You want to run Docker for our load balancers. That's a little bit more tricky. You want to run Docker for Zookeeper and for DNS servers and for databases. In fact, you want to run Docker for absolutely everything. Now, that has a few issues. So let's say that we have our data center firewall is usually the outermost thing in our data center. This is where a request coming from some poor user out there on the internet actually goes and hits. So let's say we have a wonderful service-oriented architecture, services are ready locatable, they move around, and we want to route this request to the service. So what's a data center firewall going to do? Well, the first thing it needs to do is it needs to go talk to a load balancer. Now, if we run a load balancer on Docker, then the load balancer will get an internal IP address unique to the physical host it's running on, and it bound the port 80 on the container to port 80 on the host. So yes, Docker does NAT, it does network address translation. The same wonderful technology that powers your internet at home in that tiny little $30 router you bought from your local electronics store, that is what is now powering corporate data centers. And all the problems that we have with NATing at home, you never have in the corporate data center. Not sure that's the best choice, but let's go with it. So what will our Nginx do? Well, Nginx is a fantastic technology. There's a Zookeeper plugin for it. So Nginx will go talk to Zookeeper. And hey, Zookeeper, we're on Zookeeper and Docker. So we have that running on another machine. And again, it's bound to the host. So we have said that 10.124, which is the machine that physically runs the Zookeeper instance, that's where you go to talk to Zookeeper. Now we're past the layer where we are talking about static things that can't mute, things that must be reachable. Because in Zookeeper, we will go figure out where is this service running right now. And at this point, Nginx can go down to where it's running right now and actually access the application. Now, the application itself, when it started up, had to go to Zookeeper to register itself. And this means, at this point, the application, what happens if one of these two dies? Well, then we have a problem, because my data center firewall, and we actually, well, I did ask the large corporate vendors of, Cisco, all of them that make firewalls, do you have a Zookeeper plugin for your firewall? And they look at me like I'm coming from a different planet, because of course the firewall doesn't talk to Zookeeper. That's ridiculous. It wants static IP address, that's how the rules on the firewall are. That means if I want to support moving the load balancer, well, I need to have a script running on the side, which goes and logs into the load balancer whenever we move this and changes the config. Yeah, so I have something that on the fly reconfigures the single point of failure, the most critical piece of hardware I have in the data center. Yeah. Now for Zookeeper, there are different solutions. Zookeeper, you can, instead of saying, hey, we don't put in the hardware IP address for this, we put it in DNS. So now we do DNS resolution to find the Zookeeper. Okay, and we update DNS if the Zookeeper moves. Okay, now what if your DNS server dies? So sooner or later you get back to the same problem that there are special boxes, special things that you can't touch, can't modify, and if they fail, then you have a problem. So there's usually one of two strategies employed to work around this. One strategy is you build as much redundancy into that box as you physically can. This makes the box really, really, really expensive. And the other strategy, which is most commonly employed, is you hope it doesn't break. And pure hope has carried us quite far, but every once in a while, hope is not rewarded. So what happens if we go the other way and say that it is going to fail? I guarantee you, sooner or later, every single piece of hardware you have is going to fail. So optimize for failure. Let's say that we choose to buy hardware that fails soon, and through that actually design our redundancy in a different way. Now what does that give us? Well, if I don't need any kind of redundancy whatsoever on the box, then it becomes really, really, really cheap. And I can put every single dollar I have into more CPU, more memory, more network bandwidth. I don't need double power supplies. I don't need double networking. In fact, I don't want to have any redundancy at all. And I want to have a service contract that states as follows. Well, not just that 4-hour on-site stuff. No. If the machine breaks, then I will call remote hands in the data center and ask them, pretty please go to rack 17, U7, and hook up to that server, put it into a box, and ship it by the cheapest method possible to the provider. 2 weeks later, the server comes back, you plug it back in. That's the service contract I'm looking for. And if this happens at 4 a.m. in the morning, then I want to deal with it around lunchtime. There should never be anything where you have to sort of wake up and have a heroic effort to go fix your data center. Now, what does that do for redundancy? Well, you solve that at a higher level. First of all, if you can, you run multiple instances for everything, so that if one thing dies temporarily, it's not a problem. Another one is, instead of designing for never failing, design for recovering quickly. Because the honest truth is, if you are down for half a second, nobody will notice. Now, this brings us to a few interesting design principles. The first principle we have is no special snowflakes. As much as possible, we don't want to have these machines, these proprietary boxes, or these super special servers that you can't touch. Because if you have a machine that is so critical, well, what usually happens to it? Well, for starters, nobody wants to touch it. Because if you have one tiny little typo on that thing when you're trying to manage it, yeah, that's a very uncomfortable conversation you're going to have. Best case with your boss, worst case with your customer. Second principle is we want to have commodity components as much as possible. Commodity components is really awesome for multiple reasons. For us, it's actually mostly about competition. If we have something that's built on commodity components and standard open standards, then what do you know? There's at least 4 people or 4 companies providing that, and they compete on price. This is very good for us. We get stuff cheaper. And second is, if there's at least 4 companies, well, if 2 then go bankrupt, then there's still 2 who are left that can provide us with the same exact box. Now, it may have a different logo on the front, but the stuff inside it is the same. Gives us great resiliency for the future. Next thing is fully automated provisioning and reinstall. For us, this means there should be no manual work running your data center or running your infrastructure. Because the second you need to have a human being go log in and do stuff on 2,000 servers, well, 1,999 of them, they're going to do the right thing. That last one, yeah, maybe they had a typo. Maybe there was something wrong in the provisioning. Who knows? Now, you do this a few thousand times, and what do you know? Every single machine you have has at least one problem. It doesn't scale. You need to have this fully automated. And again, back to the 4 a.m. phone calls, there shouldn't be any. Now, back to the no special snowflakes. And as I said, for us, reducing redundancy, we want it to be cheap. And cheap doesn't necessarily mean I don't want to spend money. It means I want to spend my money wisely. What it means is that if I have a fixed budget, I want to get as many CPUs as I can, I want to get as much memory as I can, I want to get as much network bandwidth as I can. That's where I want to spend my money. At the end of the day, I am a high-performance computing engineer. I like things that have a lot of power. Yeah, actually, the other place I am spending money is on power. Turns out if you have things with a lot of CPUs, a lot of memory, and a lot of network bandwidth, they use a lot of electricity. Yeah. Next is scalable. We are, as much as possible, trying to design things to scale out. That means we have a standardized graph design. If we run out of capacity in a specific data center, we call up our vendor and say, hey, build another of those exact same racks you built, tens of before. Ship it to the data center. We have remote fans just plug it in, and that's it. The rack self-installs. It adds linearly to the capacity. So we now have more storage, we have more compute power, and we have more network bandwidth. And you want to design it that way so that you can start out small and then just scale out without ever sending somebody to the data center to fix things. And it must be simple. This is something I can't stress enough. Whenever you design architecture, either be this infrastructure level or application level, make it simple. Make it simple enough that it's easy to understand. Because if it is not easy to understand, then it's actually hard to implement and hard to fix and hard to extend. And it becomes important that something is easy enough that we actually go through all of it in a 140, or actually 50-minute presentation, and have a lot of people be able to jump in and fix this and work on it and extend it. That is something that scales, and that is also something where it's easy for you people to join the company and start using this right away. And the last one, which is the one we started with, is that we want every single component to be able to run anywhere. And for us, that goes from application to databases to intrusion detection systems. Now, there's 3 parts of this, and we'll have an integrated demo at the end. One part is the one I alluded to, which is network mobility. This problem that if you kill a Nginx and you move it, well, the network doesn't move with it. The second is storage. For us, the primary driver for storage was actually databases. We wanted to be able to move a database from A to B. And it doesn't help you much to move your database from A to B and get the same IP address if you don't have the storage for it. Because if you accidentally lose 2 terabytes of data, it doesn't help that the database is available. It doesn't have the data it's supposed to have. The other great area for storage, as it turns out, is Zookeeper. Zookeeper itself, we run that in Docker. Zookeeper needs network reachability, and it needs storage. Again, it doesn't matter if you break your core on Zookeeper and move it around a little bit too much, it won't come back up. And last is orchestration, which is if you have 20,000 services, even if you have full network mobility and storage mobility, you don't want to move them around manually. And this goes to the full automation. So start with network. Sorry, I have to grab this. Give me a second. So I'm actually going to start with some of the things we have tried that didn't work for us. Getting to the end result for this was a bit of a journey for us. We jumped through a lot of the common designs. We jumped through a lot of very experimental designs before we ended up where we are. Now, the basic design for network mobility that most providers will come up with is VLANs. And you have an IP address that is located here, and you just move the IP address over here. It gets a new MAC address, so you have to do some ARQ lookups and so on and so forth, but it will move around perfectly. And yes, this works like a charm if you have a single large layer 2 Ethernet segment. Unfortunately, it's really, really, really difficult to make a single large Ethernet segment with high performance. Ethernet has a very basic rule. There shall be one and only one path from A to B. It does not support any kind of forking structure or multipath. To do that, you have to go to a higher level protocol like IP. And the problem with this is that you end up with a network design where you have small switches, and then you have somewhat larger switches, and on top of this, you have monstrous core switches. And now you're back into those really large core switches. First of all, your network solution provider is going to love you if you try to buy one of these things. That's the Christmas bonus from that phone conversation alone. And second, we're now back into those boxes that nobody dares maintain, because if you have a typo on one of these, you bring down the entire data center. So that didn't work for us. So we looked at the new cool kid on the block, which is VXLAN. Actually, can I just ask quickly how many people here are familiar with VXLAN? No? VXLAN is a solution for the layer 2 scalability problem. Layer 2 scalability, layer 2 is really appealing to think about conceptually, but it doesn't scale. So the way to solve this is you take IP, or so let's say TCP over IP, over Ethernet. That's what you have inside your container. Now to transport this, you take this Ethernet frame, and you package it in a VXLAN frame, which is actually UDP on top of IP over Ethernet. So this is TCP over IP over Ethernet over VXLAN over UDP over IP over Ethernet. There's a few violations of the OSI model here. And they have actually managed to turn your ARQ problem in reverse. Because at this point, you have a very large flat layer 2 network. But the transport between containers takes your flat network and packages it in LP, which means when your container says, I want to talk to MAC address 1, 2, 3, 4, 5, 6, well, we now have a multicast packet that goes out to your network and says, hello, I'm looking for MAC address 1, 2, 3, 4, 5, 6. Which IP address has this? Which is the exact inverse of what we have in ARQ. And we tried this. And if you buy a single network vendor, it will work. All of them have proprietary solutions that allow this to work with them alone. We did not find a single pair of 2 vendors where this would interoperate. So the technology has promise for the future, and we're really, really, really thinking that this is going to solve it at some point. But today, you get stuck with the single vendor, and you can't do there, which is VXLAN is great if all you want to talk to is other hosts that do VXLAN. But for example, our corporate firewall doesn't talk VXLAN, so I need to use a container to translate from one to the other, and that container suddenly becomes a single point of failure for my entire network. So we thought, okay, But layer 2 Ethernet is really appealing. Maybe we should just forget about it, leave it behind, move on. Now, what we did, so let me actually jump for a second into how the Docker network model works today. So in the Docker network model, when you create a container, you create one of these pairs. And this looks like, this is a VHH, which means it looks like a virtual network link. It looks like an Ethernet card that is sort of has one end here inside your container. There's a virtual cable on the other end is plugged into your host. They plug this into a bridge, which is, think of it as a software switch. And this may or may not be connected to the rest of the world. And the strategy for that is fairly straightforward. You create the pair, you move one to the namespace, then you rename it, attach it to the bridge, and configure port forwarding. This wonderful LAX technology in the host. Now, we changed it slightly, and we still start with the same start in the same way. We create the pair and so on and so forth. But we have said, hey, let's take a stay away from layer 2, and let's just say set up IP routes for this. Now, it used to be that if you use full-on IP routing, you lose all hardware acceleration. Because all of a sudden you do IP routing, which is a higher level protocol, needs the CPU to go inspect every single packet and look at it. That has actually not been the case for the past 10 years or so. These days, the amount of hardware offload you have in pretty much everything you have is sufficient that there's no difference in performance between these two strategies. And it ends up looking something like this. And if you see here, there are none of these, sort of fake layer 2 Ethernet connections. And all of this is now static routing. So this route for this thing can move around. But there's a bit of an issue with this, which is, let's say I have this 10.123, and it happens to be running, and everything's wonderful. Every single other switch, router, server I have needs to have a routing entry for this one container and know how to reach it. And okay, you can set up scripts and stuff to do that. And you can have it running here, but good news over here. There's a lot of places I have to go update routing information. And hey, this is a 4-server thing. I tried to actually draw out our full infrastructure. It gave up. There's so many cables and places and stuff you have to do. So this is a 4U rack. We don't have 4U racks. We typically standardize on 32 servers per rack. I run out of space. So is there a different or a better way to do this? I don't know. Yeah, this problem was actually solved, I don't know, about 15 years ago. If you think of how the internet works, it's not like, every time you move something on the internet, we go and update every other router on the internet. No, we have routing protocols to deal with this for us. They ping out and say, hello, I am so-and-so, you can reach me through this. And then everybody that hears this goes and says to all of their neighbors, by the way, I can reach this guy, and this propagates through the internet. Now, there's matching protocols that are designed for labs or small corporate entities. The one we happen to use is OSPF. You can actually use BGP or even RIP, if you're pressing, or any other link state or routing protocol for this. The wonderful thing about OSPF is that it's old, it's boring. It's supported by every single vendor we could find. If I went to Fry's and bought the cheapest switch I could find, as long as it does layer 3 routing, it will have OSPF support. Because it's de facto standard these days. It's something that's so old that everybody just does it. And they do it well. We did not find any problems with interoperability, and trust me, we tried pretty hard to break these things. This is one of the few things where it doesn't matter which vendor you have, what logo it says on the box, they all talk to each other perfectly. This thing is so old, so boring, that they actually worked on all things a long time ago. Now, it used to be, when OSPF was introduced, the K9 was, it is kind of expensive to compute because it actually maintains a full graph of every single service or every single IP address you have, and it tries to do Dijkstra to do minimal path for all of this. And if you have, 30 to 50,000 containers, that's a lot of work. And yes, in 1998, when you had a tiny little 15 megahertz PowerPC embedded controller on your router, that was a lot of work. Our weakest switch these days comes with a 1.6 gigahertz Intel 64-bit add-on. Takes about 15 milliseconds to do a full network reroute. It is no problem anymore. It hasn't been a problem for quite a few years. And this gives us the advantage that everything for us is a point-to-point layer link. We don't have any Ethernet broadcast domains. Everything is pure IP. Technically speaking, it looks like a tiny little internet. And we run Kible's OSPF number. I'm going to show you that a little bit later on, but it makes the configuration for this just very easy. So the way we run a container is something like this. You just run it up. We have added these two here, which is specifying that, hey, we want to have a pure layer 3 network. Please don't do the netting. Give it this IP address and just plug it into the infrastructure. I'm going to try to demo this. Okay, so we have our ping here running in the background, which, as you can see, isn't able to reach anything since I'm not running this anywhere. Uh-oh. So let's spawn up the container.
Increase the font size.
I can. Yeah. Okay, I promise there's something on the bottom here. So we're now running my little container. Now this isn't the world's best, most reactive server, but as you can see, it can ping. So what happens if I stop the container again? Well, not reachable anymore, is it? And this all happens completely transparently. I just started it, allocated an IP address, and stopped it. So, whoops. So let me actually go find another machine. So this is our numbering scheme. This is SE2 Santa Clara 2, rack 14 U8. This is rack 12 U8. So this is 2 racks away. So if I run the exact same thing here, what do you know? It's all of a sudden reachable again. And that's pretty fast. And all this does is basically bring it up and OSPF and say, hello everybody, I can see this new wonderful server, which happens to be a container in our case, and propagates through the entire network. Pros and cons of this. On the awesomeness side, this gives us hypermobility, and it gives us really quick failover. And there's no special snowflakes anymore. And we can run everything in Docker. And there's actually a wonderful initiative these days called Checkpoint and Resuming User Space. They have a proof of concept of doing live Docker migration from host A to B. One of the problems they have is that they lose network connectivity. Hey, we can actually do this with network connectivity. On the slightly more sexy side, yeah, we use a full round entry for every single container. Our network is 40 gigabit switches based on the Trident 2 chip from Broadcom. That, unfortunately, has a little bit limited hardware space. It has 128,000 entries in this routing table, and that's it. Since this is a full-on hardware entry, the second you fill up that table, you can't add in many more containers. Now, 128,000 containers is actually quite a lot. We're nowhere close to the limit yet. And we also have great faith that the next generation of switches, which should actually be arriving this year, if the president will start to believe, should have a lot more routing interest. So, how difficult is it to set all of this up if you want to do it in your own lab? Well, welcome to network revolution. These days, our switches are 40 gigabit Ethernet white box switches. Our white box switches happen to come from Dell, mostly because Dell had the best product at the time, and they were competitive on price. But we buy the hardware from Dell, we buy the software for the switches from Cumulus. So much like for a server, you buy your hardware from Supermicro, Dell, Quanta, whoever. You buy your operating system from, I don't know, Ubuntu, Red Hat, whatever you prefer, and combine these two together. The same is now happening on switches. So our switches look remarkably like x64, 64 Linux servers with 32 network interfaces. Let me see if I actually have that open here. Do you have a shell for this person?
Yeah, go on top. No, that is connected. You have this script.
Here?
Yeah. That's that. And then on you do. This here. Can you list?
You get this. If you have it handy. So this is what a switch looks like these days.
Increase the font.
Actually, I'm going to make this a little bit wider. Yeah. So it is a Linux box and has 32 network devices. You want to install a package or package. It is a Debian. It is connected to the standard Debian repositories. I can run an Xterm on this if I so choose to. I would recommend it. I tried to run Firefox on it. I unfortunately ran out of disk space. But it is a Linux box. It means that all of the management, all of the skills, all the tools you have for monitoring and checking your Linux boxes now also be on your network infrastructure. This doesn't require black belt hack through in networking. It's a Linux box. So we are actually currently waiting for Cumulus to update the kernel version because the kernel is a little bit laggy. And the reason we want this is that we want to run Docker on the switches. And the reason for this is that, hey, we run OSPF, right? So we run Quagga, the routing daemon. And every once in a while, we update the configuration or we update the version of the binaries and so forth. And one of the things about running protocols, it's kind of advantageous to have the same version running on the server. So hey, if we make a Docker image for this, we can run the same Docker image on our servers and we run our switches because they're the same CPU architecture and they're the same OS. Fantastic. It just makes the world really, really easy to deal with. Now, you do need to do two pieces of configuration. The first is you need to tell it what the IP addresses is for the interfaces. And this constitutes the entirety of our network config when it comes to setting up IP addresses. The only thing that's unique and special from server to server or switch to switch here is this, which is the identity or IP address for the switch itself. The other part you need is to set up OSPF. This is the entirety of the OSPF config. So if you take these two things, plug it into Cumulus switches, that's it. Actually, we also changed the default password. Sort of deviate from whatever's in the manual. But beyond that, that's it. That's what we've done for the config. And you do this, and then that's it. You have now a high performance, resilient, and reliable networking that allows you to move things around. Now, speaking of performance, we get performance from container to container, from east-west in the data center, in other words, as far from each other as you can, varying from 24 to 39 gigabits per second. And now, this is actually not varying depending on load. It is varying on which core you run on the CPU or on the server. All of our servers are dual socket. And if your test application runs on the socket that has the PCI Express bus, that has the network adapter, you get 39 gigabits. If your test application runs on the other socket in the server, you get 24. So our main bottleneck here is the bus between the two sockets on the server. I can live with that. Now, for latency, we have done super high scientific ping testing. That came back at 30 microseconds. We've also done some UDP low latency direct to user space testing, comes back lower, but 30 microseconds is good enough. I've yet to really find something where the 30 microseconds is a problem. Still trying though. Now, that was the data center. So here's the question I want to ask you. If you have something like this that you're running in a data center, what advantages can you use on your laptop? Well, IP mobility is actually a really fun thing because it can do it on this basic laptop as well. And it allows for really easy and rapid development. So I'm not sure that's set up on this laptop, but if you have your MacBook sitting here and you have a boot to Docker VM. Boot to Docker, if you're not familiar with it, is a ready-made thing you can download, and all of a sudden you have it's sort of a VM for you and you have Docker running on your OS X. It's a wonderful tool. So we have set up routing on my MacBook saying that 1010 whatever should be routed to the Docker VM. In the Docker VM, we have said that 1010 whatever should be routed to the MacBook. That means if you ping a random address in the 1010 space, it's going to ping back and forth here until it gets dizzy, runs out of TTL, and the packets get around. But the basic rule for all IP routing is to use the most specific route possible. This is actually what makes the hardware in your routers so ridiculously expensive, because it's not a hash map lookup. No, you have to go through every single rule, pick the most specific one, and use that. And what that means is if I'm in my MacBook and I ping 10.10.2.1, which is running in here, then the packet's going to go in here and use the most specific route, which is directly to this Docker image. Similar for this backend here. But hey, this allows for some possibilities because I can take my backend out and start it here on my MacBook. Now, if I'm now on my shell and I want to talk to the front end wants to talk to the backend, then the traffic goes like this. It goes from my shell, which is where I'm testing, sends the traffic into the Docker VM here, and then back out here again. And this allows you to have a standardized set of services that you download and run in Docker. But if you are currently developing the service, it's a bit of a pain to build a Docker image, start up the Docker image, try to attach your debugger to this thing. It is a lot more easy to just run with IntelliJ or Eclipse or whatever have you, run the service right there, and have the rest of your little infrastructure cloud running on your Docker VM. And this actually allows you to do that with static reachability, which makes all of your testing really, really easy. So next up is storage.
Okay. So we fixed the problem with the mobility. Now we can move our containers to different hosts, and the IP is going to be preserved. The routing is going to be updated, and everything is going to be working. But so I'll say, what happened if we want to run the database on a container? What happened with all the data? So there's a limitation on the Docker read-only layer of file system. I don't know if you're familiar with how Docker handles the storage. You have all these different layers of read-only file systems that are mounted one on top of the other, and you can just modify the one on the top. So this works fine, but as soon as you move the container, all the layers that are not read-only, you are not carrying those over. So the part of the images that are read-only can be preserved, can be pulled again, but all the data you modify are not going to be preserved. So we need to put the data outside the container. Still be accessible inside the container, but the data will be stored somewhere else. So we have this concept of separation between the computing nodes and the storage nodes. So I have the cluster with all containers running, but the data is lying somewhere else on different devices, different servers. And historically, this means to go to proprietary solutions and buy a big black box from EMC or NetApp, which is basically a big server with a bunch of hard disks that are going to provide you some means to access that data. This has several problems. The first is the vendor lock-in. So you buy this big black box that you can't actually repair if something goes wrong. You can call them to fix that. But again, you can have a not great SLA, so you can be waiting for 4 hours to get to fix the actual device. Yeah, at the same time, if you want to scale it, you want to add more storage, you want to add more capacity, you basically have to buy a new one or buy some expansion or some kind of scaling solution that usually is going to scale out by a bigger thing and not to add more hardware on the side, which is a scale out thing. So, aligned with our principles, we favor on our storage mobility solution to run on commodity hardware. So let's say to basically throw the server away and just put a new one. Be fault tolerant, so it doesn't care if one server goes down. We don't want to lose data, but at the same time, we don't want to treat this special server as a snowflake that can break and go down because we lose data. We want to have the ability to clone the storage, make snapshots of that, and the same way all the modern file systems allow. And we want that scaling it to be that shouldn't be really painless. I mean, it should be painless. It shouldn't be a pain to scale it, to add more capacity, to buy more hard drives and put them inside the server. Because basically, if we are talking about the storage cluster, the only thing you need to do is to add more nodes there. We also want to have full POSIX compliant file system. Have you heard of the Hadoop HDFS or even NFS? So those are not really POSIX compliant. So your application needs to be more or less aware that what file system you're running. we want our storage solution to support POSIX file systems and treat it in the same way as a regular hard drive. And it would be great if it's open source, so we are not, again, we don't want to fall on the vendor locking. So we look for Ceph. Ceph is an open source storage platform. It's specifically built to create storage clusters. It provides, on the first level, object storage. You know what's Amazon S3. You store objects on a certain name, but it builds around that several solutions, like to build complete file systems around that, or even block storage around that. Has the advantage of not having a single point of failure. So you have this big cluster with a lot of nodes, with several hard disks inside each node, and there's no single point of failure. You can take any server you want, turn it off, and the data is going to be there, because all the data is fully replicated. And also has the advantage of being able to scale it to the exabyte level, so it can actually store and handle a lot of data. Okay, so how does it work and how are we using it? This is a representation of a Ceph cluster. You have different nodes, so we call OSD. And each node contains several parts of what you call a file system. Those are fully replicated. So if you look at this, we have what you said, you have a directory on your container, which usually is mounting, well, no, usually, always, is mounting a block device that you have on your system. Actually, that block device is a representation of a Ceph image, which is this abstraction that Ceph provides to store data. And that image is stripped on different servers and it's replicated. So if, for example, I turn off the server, I still have the same data on this one. So this is not only stripped, but also replicated. So that's the way we are using Ceph. We create images, which are basically you create file systems on that. We map these images to block devices and then mount that on directories. So you do this actually on the host. Things are a bit different on a container, because what we basically want is to have the data stored here and be accessible straight from that directory. But you usually from inside the container don't have access to the block device. That's usually on the host, and so in Docker you can actually access the block device right from the container, but it requires the container to be on the privileged mode, and we certainly don't want to follow that path. So we make Docker interact with Ceph. So Rails is actually the component of Ceph that handles all this abstraction to build images and volumes on top of these objects that are stored in the cluster. So we start from this Ceph image, which is, say, in this case, is the service data. Inside that image are all the files from my database. So on the host, what we do is we map that file in a block device. Then we mount that in the host. So inside the host that are running my container, you are going to find that this folder /var Docker Ceph mount has all the data, all the file system that is inside the image. And then we bind mount inside the container one of the files, or we actually bind mount the whole folder inside the container. So this bind mount is basically just a sibling that you have between those part of the file system, and it works great. So this is actually the modifications we made. So if you remember in Docker, you mount a volume with the -p option, but usually what you do is you pass a host directory and a directory inside the container that you want to bind, that you want to mount bind. Instead, what we do is we just pass a Ceph image, which in this case is service data, and we pass what's the path in which we want to mount this data. So for if we have our database, we are going to have in this home service folder all the files that allows me to start up my database. So now it doesn't matter if we move the container, the IP is going to be there, and also the storage is going to be there, because it's not actually stored inside the container, but it's on even on a different cluster. What we added was this Ceph flag in this option that tells us that we are actually passing a Ceph image. So we can have a small demo from this. The font size is okay. Can you see?
Yeah.
So we have, this is a computation node. We use this node, this server, to run containers. From here, I can list the images that my storage cluster has. Let's point some of those. So as you can see, all those are images that stores actual file system. So I'm going to run a container. I'm going to run Docker run CI. I'm going to use this one. This is an image I created. I'm going to so I want to mount that in, say, my /service folder. I have to tell it to, hey, test or FE is actually a Ceph image. I need to mount in that mapping and do all the stuff. I can tell it, please read write. And I started with that. So my container starts, I have the service folder there. And inside that, you have all the data. It's not actually in the container, but mounted, mapped and mounted inside that. But still, all the data is stored actually on several servers, stripped and fully replicated. Okay, so orchestration. I'm going to grab some water. Okay, so now I can move my container. It's going to preserve this IP address, so the network is going to be working regardless the host I'm running it. And also I can keep the storage. So my container carries its data around, even though the data is not actually inside the container. It can be accessible from there. So the thing is, okay, I can move my container, but who is going to move it? I need a way to automatically move this container if something goes wrong. If the service goes down, or my container depletes the capacity of my server, I want it to be moved to other place. So there are several orchestration solutions. What we favor is to have Docker support. So the Docker should be a first-class citizen to be able to this orchestration tool needs to, for us. It's important to understand what the Docker container is and provide tools to favor that. It should be fault tolerant. So we need a tool to be able to orchestrate all these services. I want to be fault tolerant. Well, also this infrastructure needs to be fault tolerant. It should provide a way to isolate our containers. Even though our containers are isolated by the Docker mechanisms, still we don't want a container to be affecting the other ones. Also, when you have this amount of servers, having the monitoring and the visibility mechanisms in place, super valuable. And we would like, even though we shouldn't care where my container is running because IP address is relocated and the storage is available everywhere, we still want some ways to select where I want to run the containers. So that's what we talk about the flexible scaling, which is, okay, run this container, but I want several instances of the same container, but I don't want to have more than one instance of that in the same rack. Because if one rack goes down, I want to have the other instances on different places. So for this problem, we looked into a couple of solutions. We ended up with Mesos and Aurora. So Mesos is also Aurora are two Apache Foundation projects used right now by Twitter and several other companies. But most of the work put there are from Twitter on the Aurora part, and Mesosphere is another company contributing a lot to Mesos. So what are these things? So the Apache Mesos, what it does is you have this big cluster with a lot of servers. What it does is to abstract out where the what computation resources you have. So you have CPU, memory, storage. And what Mesos does is abstracts that out, so you don't actually care about the actual servers, and offers all these resources to frameworks willing to use it. It's a bit abstract. But what Aurora does is to take all the offers that Mesos has, Mesos provides, and select in which of these offers it wants to run my container. So if I have, I don't know, 100 servers, Mesos is probably going to tell me, okay, you have these 100 servers by the times of the number of CPUs you have. And then Aurora selects in which of those servers, but not actually selecting based on the physical server, but on the attributes it has. It's going to select one of those to deploy my container. And it also provides some mechanisms to do monitoring of these containers. So if one container goes down, it starts up. It basically works like Upstart or systemd, but across my data center, and not only one system. This is how it looks like. So to Aurora, I have this concept of job. A job is basically a container I'm starting and I want to run. So for example, my database is running inside the container. So I say to Aurora, okay, run this new job, which is based on this Docker image. And it's going to need these resources, 2 CPUs and 1 GB of RAM. And I need to have 3 of those guys. So it doesn't matter if maybe I have a different service running a load balancer that's going to point to these 3 instances. I don't care if one of them goes down because I still have 2 spare services. So I tell Aurora I want to run this job. What Aurora does is it talks to the Mesos master, which is a server that is replicated in case it goes down. It still has several instances running at the same time. All those coordinated by zookeepers, so you only have one leader, one active master running. And in the case it goes down, another master takes the lead of that server. So Aurora is going to tell the Mesos master, okay, what resources can you offer? And the Mesos master is going to provide all the individual offers of all the servers in my data center that I have running as Mesos slaves. So this Mesos slaves has, I don't know, the node 1 has 32 CPUs and 256 gigabytes of RAM. It's going to offer that to the Mesos master, and the master is going to offer that to the framework, in this case, it's Aurora, and offering to Aurora So this is the dashboard of Mesos. There we set up a small cluster. You can see at the here on the left, it's telling me which resources it has. This cluster has yeah, the idle thing. I can fix
that a
it.
bit more. It's definitely way too idle.
Yeah. Yeah. So it's telling me that it has 864 CPUs and all this amount of memory available. Here is what I'm using. I'm using just 4 gigabytes of 6,000. And I can see here what are the slaves that are running on my cluster. Actually, 20 something slaves, and these are the offers that Mesos is doing to the frameworks that are going to use it. So it's offering, for example, this host, which is on the rack 16, the unit 8, has 32 CPUs and this amount of memory and this amount of disk. You can see that we don't have much storage here because all the storage is handled on the self cluster. And it keeps track of all the slaves that are given this software. So frameworks. Here are the components that are going to use these guys. This is the actual class name of the Twitter scheduler, which is part of the Aurora. So let's use this to launch a new task for Mesos, a new job in Aurora, a new container, and see if it appears here. Okay, so here, what's actually a task in Aurora? As I showed you on the slide, it's something like this. It's a text file with a DSL based on Python, which I have defined a couple of variables here. What is the service name? What's the Ceph volume I want to mount? Which IP address I want? And what Docker image I want to use. I'm also telling him to use 10 gigabytes of RAM from the Mesos cluster. And I'm using those variables right here, which is basically a way to define a new job. We made a couple of modifications here to support the modifications we made on Docker. So now Aurora understands all these net parameters and these Ceph volumes we are using. So I can actually create the task. Now let me show you how to create one. So I can tell Aurora, okay, create a new job with this name. It actually uses a schema in which it identifies the cluster name, the role in which we want to run the container, and which environment, it can be production or whatever. The number of the name, sorry, of the service, and the file with the definition. So if I can run one, just like this, create the C2, okay. So there's some debugging information there, but at the bottom you have this message saying that the job was created. The job was successfully created, and it gives you a URL that you can use to actually access the Aurora dashboard to see how your application is running. Okay, since a few seconds ago the container is running, it's running on this host. You can see the configuration of this job. And if we go to the actual host, we can see that it is actually running the container. So it's on this one. If I do a Docker PS, I can see that this is the image I want to run. This is actually the name of the container. That's the name Mesos dash and the code that Mesos uses to track it. And if I go back to the Mesos dashboard, I can see that my demo.
Just the wait was, I think.
Yeah, the demo DB is actually running since 2 minutes ago on this guy. We can use this as a way to see the logs of this container and see what's doing inside. But the particular thing here is that this container is actually running on this R16 unit 8. I can access it. I'm going to here. So I wanted to deploy a Postgres database on this IP address. So if I go here, if I go in that, right, Postgres is going to answer me. I can see that I have a couple of databases there. I'm going to connect to this DB. And I have a T table with a hello world. So my database is up and running inside a container, and the data is not actually on the container, but inside the Mesos image that is actually mounted in the container. So let me. So this is the actual server where this Docker container is running. So what happens if I shut down it? Let's reboot it. hope it works. Or something else. Okay, it's done. It's done now. I'm back on that. So emergency. Picture trying to. If I go here, I see that change it from 16 to 17. Actually moved the container to a different rack and started it just in a couple of seconds. This guy should send someone to turn it on.
Tomorrow.
Okay. It's a spirit. And what's happening here? If I select again, so the connection to the server was lost. It's attempting to reset the connection, it is succeeding. So if I run the query again, it's going to work. So the guy switched from different racks, started the container again, and the storage kept the data set. Yeah, I think that's it.
Yeah. So what this gives us is the ability to really run absolutely everything we want as a service. It can be moved around. And unlike this wonderful little toy thing you have on your laptop or on the whiteboard, this is a real production. Actually, this isn't the production environment. I'll mention that we don't generally hot reboot stuff in the production environment willy, but this is the same architecture we use for operation systems. And it really has that wonderful flexibility that it just works. And you don't need to decide for these strange occurrences. And here's the thing. Anything that you run in a data center that has 1,000 servers, if there's anything that is extremely unlikely, I will guarantee that it happens at least once a week. So that's it. I think we'll turn it over to questions at this point.
I have servers that doesn't run on Docker, like that maybe runs Cassandra. And it seems to me overkill to have like Cassandra that does the replica thing and have a Docker and have everything duplicate, and on top of it, or have mesos and everything. Just like I'm feeling like old school that I don't like these multi-layers. Do you have any kind of database or service that you are running this way? Because I understand Postgre, but do you have any Cassandra or anything?
We have a Voldemort.
Okay.
Which is not Cassandra, but we do have Voldemort running that way. And you're absolutely correct. It is complete and utter overkill to have, which typically does 3 replicas of old data. And on top of that, have a Voldemort, which does 5 copies of data. So we now have 15 copies of the data. We feel really secure. But it is overkill. The question then becomes, okay, so what do? Do you want to set aside a set of pool servers that will have enough storage to be your Cassandra relocatable target? And let's say you do. Now you shut one of them down, you start your walk over here. It still has to copy all of that data. It has to rebuild core. That's a lot of data to copy. That is one way to do it. We chose to simply say, no, we unify. Most of our databases is not Cassandra, it's not. So for us, this makes more sense. Most of our data is of this more tangible, smaller thing. But it's absolutely possible to have a pool of compute nodes that have enough local storage. Our compute nodes have the cheapest SSD we could buy at 100 gigabytes each, not really suitable for running Cassandra on it. Yeah, for us, it's about unified infrastructure. Everything is completely identical. Oh, you give everybody who has questions a t-shirt. Oh, I'm screwed. Other questions? Okay, more t-shirts.
Okay, I'm going to have a store of t-shirts, 7 t-shirts. I don't know if you tried, I understand that you have everything on premise, but have you tried Amazon Container Service?
I tried Amazon Container Service. That's as far as I've gotten with it. For us, Amazon is not cost effective since we are an enterprise software company, and our users expect the same level of availability and resiliency, and in fact, everybody being able to scale it at 4 a.m. in the morning as they do Monday morning, which is when they have the high speed. Since we have so many servers that have to be on 24/7 to just meet this enterprise speed mode, Amazon is not cost effective.
Okay. Last one as well. How do you keep track of our image? Like, do you have anything like Puppet or Chat to build your image?
Actually, we built it with Bamboo, not with Puppet Chat.
With what?
Bamboo. It's I think it's a competitor for Jenkins. So it's we have already basic pipeline, which is mostly working at this point. Which is we have most of our repositories on GitHub, and anytime you create a new repository on GitHub, it automatically creates a matching project in Bamboo. And if your project on GitHub happens to have a Docker file, then it will build a Docker image of it and push this out for Docker repository.
Okay, so you just use the Docker file to define, like, I don't know, get this code. And
yeah. The Docker file is a makefile for Docker images. And the basic pipeline there is that if there is a Docker file, then you will build a Docker image as part of the automation.
And then you don't fall short because it's really simple what you can do with a Docker file.
Yeah, it's actually ridiculous and simple what you can do with a Docker file. And Bamboo happens to be the stuff that we use for, or are going to use for most regular tests. So it already needs to be able to build this thing. So this is actually wonderful news because it means it's the same buildable artifact that we use for testing, for integration testing, for running on your laptop if you want this cloud, and it's the same thing we eventually push to production. So it's unified everything. Makes for a lot less surprises.
If you guys want to ask questions in Spanish, it's okay too.
Yeah.
I have a question. The maximum amount of memory that I can submit into a cluster is equals of the maximum amount of RAM into a node, like the data source scheduler of the.
Right.
Okay.
Otherwise, it's going to be actually the job is going to be still in there, waiting for a piece of software able to cope with that amount of memory.
The amount of memory that is available in.
Yeah. So then you see the memory aggregated, but actually there's a lot of offers of the maximum amount of memory of each node.
That just happens to be the sum of it all. So if you saw our nodes are standardized in 256 memory, so if you ask for 300, it's going to take a while before that becomes available.
This is Aurora. Say you have two slates, right? 10 gigabytes from each. You have two jobs running actually, one that's of 5 gigabytes, the other one of 4 gigabytes in different states for some reason. And now you have a job that uses 10 gigabytes. Does the rest of Aurora realize that they can shut down the core and start the other one temporarily? It will just take storage ahead?
There's no support for that at the moment. And what you're actually alluding to is the online bin packing problem, which is that unless you have perfect knowledge of the future, you cannot do ideal placement of the jobs you already have. But this is actually why we talked about checkpoint and resume in user space, which is the ability to take something that's up and running right now and move it live. If we teach Aurora about which services we are able to tolerate a 1 second blip on, then we can tell it to, hey, shut it down over here, move over here, because I want you to free up more space. So you can basically do container repacking of your data center to optimize resources. There's no support for that in there at the moment. We've talked about the possibility of adding it, but that's as far as we got.
I'm sorry. So we don't know instance. So, if you're using MySQL or Postgres as you use it, the idea is that you cheaply are going to use a master server database available, something like that.
We could. Actually, it's an interesting point, especially when it comes to, well, let's say we do master for availability. So these two masters have to know about each other.
Yeah.
And if one of them goes down, I am now down to a single point of failure. If the other master at this point goes down, I have lost the data for my customer. There might be transactions which I have now acknowledged to the customer have been there, and I lost both masters. That means when the first master goes down, that's a critical data center event, and we have to send somebody to the data center right away to fix it. So having something like this where there's no such thing, just to start up another one, you can still run master on top of this infrastructure. But at that point, you do that for additional capacity, or for linear scalability, or scale out if you want, more than you do for redundancy.
Okay. So the redundancy is kept by Ceph, and you are
yeah. So the Ceph part is about the ability to move the masters around. So that means if one of the masters fail, it just starts somewhere else. And you have, let's say you have just master. Let's say I have master. So I have now 5 of them, but I do so mostly for capacity more than I do for resiliency. It makes it really, really easy to scale. Now, about, say, MySQL or Postgres, that's an example of 2 technologies that do not have a built-in Zookeeper client. So if you are in the Postgres world, a slave and a master, and I move the master, I have to go, remember to update the config on the slave. If you forget to update the config on the slave, you do not have a backup anymore. And it's a bit of a nasty surprise when the master at some point dies, and you figure out that I forgot to update the slave a week ago. This is when you really, really scramble to the data center and try to salvage those drives. And you drive fast.
About security, did you find any barriers working with engineers, having this dynamic scenario, trying to convince them that your is a good stuff?
Interesting question. Yes. We did. We actually brought in our security team. They brought in addition to the team they have, a lot of outside consultancy and outside people to have a look at this, since we're going in a very different direction. And we do have clients that have hard requirements that they shall not be co-located in any way, shape, or form with other clients on the same physical hardware. This is where Aurora is a wonderful thing, because you can tell that, hey, this thing shall not be co-located with anything else. Now, that happens to be paper security. It doesn't actually add anything to your world of security. For the containers themselves, we run the containers as lean as possible, which means inside the container, you have the Postgres database. There's no secure shell daemon running in there. There's no system tools. There's nothing else. There's only the Postgres database. This is something your security people love, because it means that each and everything you run does one and one thing only. If you are in a classic VM-based, for example, solution, then your Postgres database VM also runs a secure shell server. Typically has, hey, what do you know, it has a mail server because it needs to send out system logs and so on and so forth. It has also these additional things. Another thing that our static IP allocation system actually does support is to say that, hey, this client shall only exist within this IP range. And now you can actually add standard IP tables rules on the host saying that to this container, you can only come from this IP range. So you can do a full layer 3 network segregation on your containers, which is something that's really difficult to do in the internet. But you lose the ability, for example, to run VLANs. So you have to do a little bit of explanation to the security team of your clients when you try to explain why this is different, why you're not using the standard technologies for this. But the end result is something that actually has a lot better and more scalable security. So,
how did the servers find this out there?
Ceph has something that looks remarkably like Zookeeper. It's known as a set of monitors, and you have to connect to one of the monitors. And hey, we run the monitors in Docker, so they're relocatable. So they each of them, the monitors have a static IP address, and if that box dies, then I'll start the same service over there. So this idea of running absolutely everything as a relocatable service actually opens up a lot of interesting possibilities.
Can I find this stuff on GitHub?
Yes, you can. Let me actually. So all of this, all the modifications you just seen, all is on GitHub. You can download it, play with it, run with it. I'll try to find some way to share our presentation. I don't know if there's a mailing list or something you can send it to.
We can download the presentation too.
Yeah, we have no problem sharing that. So I'll plug into you after to distribute. Yeah. And as much as possible, we want to be able to actually help you guys set this up. So if you have questions on this, that you want to try it on your lab, just send us an email at that address, and we'll answer any questions you have.
Okay.
How do you manage logs?
So actually, there's two ways of doing this. One is you can go here and inside the sandbox of, I don't know, where's our database for these days? Actually, what did you do to this response? What did you do? Okay, when it's normally working, you can click on the sandbox here, and that will show you all the system logs for that standard out, standard errors, and so forth for that instance. Now, that doesn't really scale quite as well as we would like. So we're now moving a little bit above the infrastructure level, but we're setting up Kafka-based logging regression, which then pipes it all to add cluster tree visualizations, also for one files.
So you need to have, for instances of my service line.
Yeah, you will be able to look at them in conjunction. Yeah. Now, that works great for anything that uses, say, log4j. Postgres, again, no Kafka-based plugin for that one. So then you're back to this, and now you have to look at the logs here. Actually, Postgres is an unfair example since it has very persistent data stores, so we can actually look at the logs inside a file system. But yeah. Other questions, guys? Come on.
Kafka is also running.
Yes, we run Kafka in Docker image. As I said, we run absolutely everything in Docker image. If I could, I'd run Docker in the Docker image. Yes and no. You can, but you don't have to run it remote over X11. I wouldn't recommend that to anyone. Yeah, I was kind of hoping there were more questions.
What to a scenario where you just show me as a developer or you can program on your laptop? You could find a way to, for example, start resources on your local machine and then shut it down and consume it from the sandbox in the data center, for example. So I can have a partial environment. Maybe I don't want to run the whole thing.
Yes.
On my
We have a partial proof of concept for that. We haven't actually rolled it out yet. So far, our service cloud is small enough and our development laptops are big enough that it's not a problem. But at some point, it will be. At some point, you will actually need 200 services running just to get a very, very basic thing up and then started. At that point, we will absolutely support having basically you say to your Q&A center, spawn me up a complete cloud. It will do so, and you say, and by the way, redirect that service to my laptop. And the same reachability, the same routing tricks will at that point have all these services connected in the QA cloud talking to each other, except when they talk to the specific service, which is routed out to you. Network routing allows for some really fancy stuff.
Trying to run a support inside a switch using Docker. What is I didn't understand exactly what you meant.
It's about having the same artifact for everything. Same as we do for an application. You want to have the same artifact for testing, for rolling out, for production, for building. If we can on the switch run Docker, then we can have the same binaries for logging, for monitoring on servers as we do on switches. It's just we can do the same by using debian packages, which is what we do today. It's a lot more convenient to use the Docker images.
So, are you using any kind of orchestration regarding the load balancer when you are in some kind of deployment scenarios in order to avoid losing package or avoid downtime? Are you doing something with the load balancer?
So actually, as we can see here, there's a Medallia from Nginx QA, and that would be a load balancer. That's the Docker image. Now, if I understand your question correctly, it is how do we avoid losing an in-flight request during the middle of deployment?
Yes, yes. I think I am trying to avoid the proof of the load balancer going to add to the container it's alive and failing and losing packaging.
So Aurora has partial support for this, and we actually have a little bit better support for it. But it's to tell your service to fail its health check. And if it fails in the health check from the load balancer, then the load balancer will stop sending requests to it. Now there will still be stuff in flight, so you basically tell your service to do the following. First of all, start answering negative to the health check answer. Finish all pending requests, then exit. At this point, Aurora will say, it's dead, and go restart it or redeploy it somewhere else. But this has to be handled at the application layer. There's nothing in the world that will protect you from having lost an in-flight request if it's half served by the application. Okay, in that case, I think I'll say thank you. Oh, wait, listen.
Yes.
Yeah, if you guys want t-shirts, Mana is still.
Thank you, guys.
Still out. We also put this in like someone.
Yeah.
Put this in working on this type of stuff. Talk to any of us for water too. And there's still some beers. We're gonna find out here. There's still plenty of time to discuss and talk about this.
Yeah.
So,
I'm gonna hire you.
I'll get hired. Yeah.
Hey, how do you do this thing? Yeah.
So there's your website, your.
It works. That's a nice thing. You know, Docker is fantastic for developer. It's built by developers for developers.